Hello everyone, I'm Chen, and today I'll be presenting my work Novel View Acoustic Synthesis in collaboration with Alex, Roman, Vamsi, Natalia, Kristen, and Andrea. Please wear your headphone to hear the spatial sound. Many of our important life moments are recorded in videos. For example, this is a cute moment of a baby talking to his parents. However, videos are passively collected from one viewpoint, thus limiting us from viewing the video more interactively. If we want to relive this moment in a virtual and augmented reality, we need to be able to synthesize the video with sound from arbitrary locations in space. Novel view synthesis has gained lots of attention in the past few years, especially pioneered by Nerve. However, it is by far vision only and does not handle sound. How do we synthesize the sound for novel viewpoints? Motivated by the application and limitation of the existing work, here we propose the novel view acoustic synthesis task, where given the visual and audio observed at the source viewpoint, conditioned on the relative target viewpoint pose, the goal is to predict the audio waveform at a target viewpoint. This task is very different from novel view synthesis due to many reasons. In novel view synthesis, the 3D scenes change limitedly during the recording, while sound changes substantially over time and is highly dynamic. In novel view synthesis, the camera captures light in a highly directional manner, while the microphone array are at best weakly directional, since one microphone only measures one point of the acoustic field in space. The frequency of the light is also very high, providing enough spatial resolution for triangulation and segmentation, while the audio frequency often spans across a wide range of spectrums. Lastly, sounds are often mixed together, with the background sounds or reverberation which are affected by the space differently. Due to these reasons, it is not possible to apply novel synthesis models directly, and also there is a lack of supporting dataset and benchmark for this task. In this work, we collect two datasets as well as propose a new model to tackle this problem. We first collect the replay NVAS dataset, where we capture 46 scenarios from 8 different viewpoints. Each viewpoint is equipped with a DSLR camera and a binaural microphone. We have 2 to 4 actors acting on certain topic in each scenario. For example, having a conversation, doing yoga, having a dinner, and etc. Each actor has a near-range microphone mounted on their chest to record their voice. In total, we collect 37 hours of video data. In this example, we show for one conversation scenario, the viewpoint shifts among 8 DSLR cameras. Notice how the sound changes according to the pose of the camera, the distance of the active speaker, and their orientation.
Studying dance? What's she studying? No, she's trying to study criminology. Whoa! Yeah. But that's super different. Yeah. Oh, because she's like really, we're both like really into true crime, but she's like more.
In addition to the raw data that is collected in one room with a pretty fixed camera setup, we also construct a synthetic dataset based on sound spaces too, which gives us the flexibility to change environments, speakers, and their locations, sound spaces to render acoustic effects such as direct sound, reverberation, transmission, and diffraction. We use labeled speech as the source audio. In total, we collect 1,000 speakers, 120 3D scenes, 200K viewpoints, and 1.3K hours of audiovisual data. In this example, we first play the speech spoken by the active speaker and then the audiovisual observation at different viewpoints.
You know, I thought the dance a bit conscious tonight, for the first time. You know, I thought the dance a bit conscious tonight, for the first time. You know, I thought the dance a bit conscious tonight, for the first time. You know, I thought the dance a bit conscious tonight, for the first time. You know, I thought the dance a bit conscious tonight, for the first time.
Next, we present our method named Visually Guided Acoustic Synthesis, or short as VGAS, The key idea is to learn an implicit neural transfer function that reasons the sound source location, acoustics of the space, and the target pose in 3D to synthesize the target sound. Given the input audio, we first separate out the ambient sound to focus on the sound of interest and encode it. We then localize the active speaker on the 2D image based on the near-range microphones. We extract the visual features and concatenate it with the localization bounding box and the target pose. We feed the audio and visual features into the acoustic synthesis network, which has several stacked fusion blocks. In each block, the features are processed by dilated 1D convolutions and dot product for fusion. Altogether, this network is supposed to learn the transfer function that transfers the audio from the source to the target. Lastly, the previously separated ambient sound is added back to the waveform. During training, our temporal alignment module shifts the prediction by the amount of delay estimated between the source and target to align the prediction better with the target. We encode both the prediction and target audio as magnitude spectrum and use an L1 loss to minimize the distance. For evaluation, we look at three metrics: the closeness to the ground truth, the correctness of the spatial sound, and the correctness of the acoustic properties. We also experiment with two setups. One is single environment and one is novel environment. The second is to evaluate the generalization of the model. We consider four baselines when copying the input. Two baselines are based on the signal processing, and one baseline is recent generative model for matching acoustics with images. Here shows the results of our model on two different datasets. Our model outperforms all baselines, including the audio-only ablation. We'll also find that generalizing to the acoustics of novel environments is pretty challenging. Here we compare Vegas with three other baseline methods on sound spaces NVAS.
You know, I thought the dance a bit conscious. You know, I thought the dance a bit conscious. You know, I thought the dance a bit conscious. You know, I thought the dance a bit conscious. You know, I thought the dance a bit conscious.
In this example, we show that for one source viewpoint, our model predicts the audio for four different target viewpoints.
Did not Christ himself say? 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 Did not Christ himself say?
Next, we show two examples of the model prediction on replay NVAS. We first played the source, target, and then our prediction.
Like soccer, just like you're not allowed to use your hands. Like soccer, just like you're not allowed to use your hands. Like soccer, just like you're not allowed to use your hands.
All right, heads on. All right, heads on. All right, heads on.
For more details, please check out our project page. Thank you.